So we're going to do two more applied optimization problems here. One with vertical motion and then another with average cost. So vertical motion, let's read the problem. The height above the ground of an object moving vertically is given by S equals negative 16t squared plus 96t plus 112, with S being measured in feet and t being measured in seconds. So S is my position function. It represents the distance or place of this object at time t. So let's read the rest. We want to find the object's velocity when t equals 0. We need to find its maximum height and when it occurs. And then also we want to find the velocity when s equals 0. So a couple things that we know, we've learned already this semester. When we're dealing with s, our position function, we know that s prime represents v, velocity, and s double prime, or that first derivative of velocity, would represent acceleration, in case you see that in there as well. So we want to find the velocity when t equals 0. In order for us to develop a velocity equation, velocity is the first derivative of position. So for part A, I'm going to say that v equals negative 32t plus 96. So that is my velocity equation. And the velocity when t equals 0 is negative 32 times 0 plus 96. V of 0 equals 96. So that means the velocity, the initial velocity at t equals 0 seconds is 96, and that is feet per second. And you see that 96 showing up in the problem. All right, so that's my answer to part A. Part B says find the maximum height and when it occurs. So maximum, this is our optimization part, and the maximum occurs when the derivative is equal to 0. In this situation, derivative represents velocity. And so if you imagine something traveling up, it has a positive velocity, it reaches its max, there's a brief second where it's not moving, the velocity is 0, and then we start traveling down. We would have a negative velocity. Okay, so part B, in order to solve this, we're going to take that derivative, v, which is s prime, and set it equal to 0. So 0 equals negative 32t plus 96. So subtract the 96, divide by negative 32. I've got t equals negative 96 over negative 32, which gives us t equals 3. So it reaches the max at t equals 3 seconds. So what is the max height? So now height is position. So that means I need to take this 3 and plug it into my position function here. So s of 3 is negative 16 times 3 squared plus 96 times 3 plus 112. Evaluating this, I get that s of 3, I get a value of positive 256. So answering part B, we'll say the max height is 256 at t equals 3 seconds. All right, and remember the max or min value is y. It occurs at x. So part C here says that we need to find the velocity when the position is equal to 0. So that clearly says set s equal to 0. So we've got 0 equals negative 16 t squared plus 96t plus 112. So we need to solve this equation. I can factor out a negative 16, which gives me t squared minus 6t minus 7, dividing by negative 16 on both sides. That would go away. 0 divided by negative 16 is still 0. T squared minus 6t minus 7. This factors, and I end up with t minus 7 and t plus 1. So the position is 0. The position is 0 at t equals negative 1 or positive 7. And in this situation, is it possible for us to have negative time? No. So at 7 seconds. Okay, so what is the velocity at 7 seconds, right? Find its velocity when position is 0. So the velocity at 7 seconds is negative 32 times 7 plus 96. So V of 7 equals negative 128. And what this tells me is that it is moving down 128 feet per second at t equals 7 seconds. All right, so let's do one other example here. Let's find a specific production level. So suppose we have C of x equals x cubed minus 20x squared plus 20,000x, which is the cost of manufacturing x items. Let's find a production level that will minimize the average cost of making x items. All right, so reading through our problem here, we have a cost function. C of x is the cost of manufacturing x items. So x is items, C of x is cost. And what we want to find is a production level. We want to find how many units to make that will minimize the average cost. All right? I know we've talked about this previously in class. One thing that we know is that average cost, and we oftentimes in math use a bar across something to represent average. Average cost is going to be the cost divided by the number of units. So C of x bar equals that cost function C of x, x cubed minus 20x squared plus 20,000x, all divided by x units. So my average cost function, when I simplify this, I get x squared minus 20x plus 20,000. There's an extra 0 there. So this represents my average cost function. Okay? So this bar means average, and average means we take our cost function and divide it by the number of units. So if we want to minimize this, finding a max or min means we take the derivative and set it equal to 0. So I'm going to find my derivative, c prime of x bar equals 2x minus 20. And if I set that equal to 0, 2x minus 20, I'm going to add 20, divide by 2, I get that x equals 10. So at 10 units, my production level is minimized for the average cost. All right, and so that's all this question is asking us, is find the production level. So we only need to produce 10 units. But what is the average cost? So C of x bar, if I want to find that average cost for 10 units, we'll be plugging 10 into my C of x function, not my derivative. If I plug 10 into my derivative, I'm going to get out 0. So that would be 10 squared minus 20 times 10 plus 20,000. So C of 10 bar is 19,900. That is the average cost at 10 units. All right, and then just expanding on something we talked about in our last video, prove that this is a minimum. So we can use the second derivative test to prove extrema. We have a second derivative test for extreme values. And what that says is I'm going to take my second derivative, c double prime of x, and I get out 2. So if I were to plug my 10 into this function, c double prime of 10, my output value is 2. And when I have a second derivative is positive, right? The second derivative is positive at my critical number. Then that means this critical number represents a minimum. Okay?